Everyone, Mr. Graham here. I just wanted to give you a short video kind of introducing you to some of the lab equipment that you'll definitely see in this class, whether it's on video or in person. And you'll probably be using similar equipment when you go to university and study physics or engineering in university. And I'm also going to give you a brief overview of how to solve a physics problem using a real-world example. I'm also going to kind of refresh your memory when it comes to some of the science that you learned about in middle school, specifically Newton's laws of motion, and specifically Newton's first law of motion. Now, hopefully you remember what Newton's first law of motion is. It's the one that says an object at rest tends to stay at rest, and an object in motion tends to stay in motion. Now, I like to call that the little kid or the middle school version of Newton's first law. We will definitely use a more rigorous version of Newton's first law in this class, and I've written that on the board. Newton's first law of motion, the big kid version, says that in the absence of a net external force, an object at rest will remain at rest, and an object in motion will continue to move with constant velocity in a straight line. So that's the big kid version. And there's some things I want to point out. In the absence of a net external force, that doesn't mean that there's no forces. That just means that any forces that are present are canceled out. So you can think of pushing on an object from either direction. If I take this scale and I push it this way, it moves that way. But if I push it that way and I have my hand here pushing this way, I'm pushing on this object. There are definitely forces acting, but those forces are being canceled out. They're being balanced by each other. And so we would say that the net external force in that case is zero. So that's the gist of it. That's Newton's first law. There goes the bell. That's Newton's first law, the big kid version, and we will actually condense this down in about a month. In about a month is when we're really going to start digging into Newton's laws. Before that, we have to study motion a little bit first, which will start at the end of this week and the beginning of next week. So I am jumping the gun here a little bit, but I like to use this demonstration just as a way of introducing how to solve a physics problem, again, with a real-world example. So what we're going to do, I already did this. I used a random number generator to choose how many of these masses I'm going to load on this cart. So this cart here, it's something that we'll be using. It's a very low friction cart, has very low friction wheels. If you spin those wheels, they'll spin for quite a while before they stop. And I'm going to put this cart on this track here that's at an angle, that's at a random angle, and then I'm going to load these masses on it. And obviously if I let go, it's going to roll downhill, as things tend to do. So what I want to do is determine exactly how much mass I need to put on this mass hanger so that when I hang this mass hanger over this pulley, it will actually balance the forces. And so I will have a net external force of zero, I'll be in the absence of a net external force. And when I let go, it will not roll downhill. Now you could say, well, you could just use trial and error to do that. Well, if you're using trial and error and just putting masses on here until it doesn't move, you're not doing physics. So we're actually going to calculate exactly how much mass needs to be on this mass hanger in order to prevent the cart from sliding down the hill, rolling down the hill. All right. So that's the equipment. One thing I want to stress is the importance of making measurements. We're going to have to measure the mass of this cart plus the masses that are on top of it. We're going to have to measure the angle of the incline here, and then we will calculate how much mass I got to put on this hanger. Well, I will calculate, and you will definitely be learning how to do this. I'm not going to ask you to do this anytime soon, anytime within the next few weeks, but after that, you're going to be learning how to do these kind of calculations. So the first thing I'm going to do is make some measurements. I've got to make measurements of the mass of the cart and these 5 masses put together. I'm going to use the scale here. I could, if I had a sufficient scale, measure the mass all at once. But this is a pretty sensitive scale. You can't put too much weight on it, so I'm going to have to measure these two separately. And I will write these on the board. And to delineate which is which, I'm going to call the mass of the cart. I'm going to call it M with a subscript cart. You always got to write down your measurements so you don't have to keep remeasuring. And it's 0.4887. What are the units that we measure mass in? Kilograms. Kilogram is the base SI unit for mass. It's not gram. Gram is still a useful measurement. That's what you use most often in chemistry. However, the kilogram is the base SI unit. The kilogram, hopefully you remember, is 1,000 grams. So the mass of the cart is 0.4887 kilograms. And then I'm going to have these additional masses that I'm going to load on the car. And those additional masses, which I will call M with a subscript ADD for additional, is 1.2704 kilograms. 2704 kilograms. And then I also said we need to measure the angle here, the angle that this ramp makes with the horizontal. I got this nice little angle indicator here, which I can measure the angle. And it turns, you have these on your phones too, so if you're in the lab, you can use your phone. And that angle looks like it's about 23 degrees. And if you remember from your geometry class, the variable that we use for angles more often than not is theta. It's just a circle with a line through the center. And maybe not a circle, maybe a 0. And that's going to be 23 degrees. We use degrees more often than not in this class, although radians would be fine as well. But my angle indicator does not measure radians. Okay, so those are the only measurements we're going to need in order to do this calculation. What I want to do, though, is call this a single object. This is a single object. I'm going to call this guy M1. And M1 is just going to be the sum of these two. So M1 is going to be the sum of those. Let's see if I can do addition. I don't know if I remember how to do addition. 7 plus 4 is 11. Carry the 1, 8, 9. 8 plus 7, 15. Carry the 1, 4, 5, 6, 7. And 1 plus 0 is just 1. So my mass M1 is going to be 1.7591 kilograms. And so what I'm going to do is I'm going to call this mass hanger plus any additional mass on it, I'm going to call that M2. And when I'm writing down what I'm looking for, I like writing M2, or my unknown. What I'm calculating is question mark. That's what we're looking for. Okay. Now, I'm not going to go through the specifics here because, again, we're not going to learn this for quite a while. But one thing you want to know, one of the first things you want to do in any physics problems, if it makes sense, sometimes you can't draw diagrams, but more often than not, when you solve a physics problem, drawing a diagram is definitely helpful. And so I'm just going to diagram the situation. It doesn't need to be to scale. So here's my ramp here. Here's my cart, which I called M1. Here's my pulley. And here's the hanging mass, which I will call M2. And they are all going to be connected by a string. Note that my diagram doesn't look anything like the actual situation. That's because I have no artistic ability, so I'm not going to take time to try to draw it accurately. I recommend you don't either. This diagram would be enough. Now, to apply Newton's first law on this diagram, I have to show that the net external force is actually 0, or any forces that are there will actually balance out. What forces are actually acting on M1? Again, this is something we will learn, we will spend a lot of time on in the coming months and throughout the year. There are 3 main forces that are acting. There are some other smaller forces that we can pretty much ignore here. But I have the first force that everybody knows, the force that actually wants to get that car to roll downhill. That's the gravitational force. And to indicate a force, I will do so just by drawing an arrow. And we know that the gravitational force points straight down. And so we will call that the force of gravity. I'll label my diagram with this. We'll learn how to be a little more succinct with our labeling of forces in the future, but for now I'm just going to label what the forces actually are. And then I have the string pulling up the ramp on the mass itself, and so I like calling that the tension force. When you pull on something with the string, that string then pulls on the object with tension. So I'm going to call that the force of tension. And those are only the only two forces. If these forces were the only two acting, the object would actually be moving. So there's another force here. And it's kind of a mysterious force that not too many people think about, but it is the force that's keeping me from falling down into the earth right now. It's the force that's keeping you from falling down into the earth, whether it's provided by the ground that you're standing on or the chair that you're sitting on. And that is, I'm not going to give you the technical name for it, but it is essentially just the force that pushes up on you, right? If the floor were to disappear right now, I would accelerate downwards. The gravity would pull me downwards. So the force that is balancing, the force that is balancing the gravitational force, providing that net external force of 0, is what we can call just the surface force, the force that the surface exerts on you. And it turns out that the surface force is always perpendicular to the surface on which the object is resting. So I'll just call that the surface force. So I have three forces, and these forces must all balance in order for the cart not to accelerate up or down the ramp. And if that's the case, then Newton's first law will apply, and the object will remain at rest. Now, from this diagram, I can set up equations. That's what we do in physics a lot. We describe physical reality with equations. I'm not going to go through how we do all these calculations now. This is something we'll learn in the future. But when I set up these equations, they then simplify to this very simple equation. The mass of M2 will be equal to the mass of M1 times the sine, your trig, your SOHCAHTOA, the sine of the angle of elevation of the ramp. And I did forget to draw the angle here, but this is the angle of elevation of the ramp. This is the equation that we end up with when we apply Newton's laws, Newton's first law, specifically to this particular situation. Again, how did I come up with this? I'll teach you that. You'll learn that this year, and that'll be one of the main things that we learn about when we study Newton's laws, how to set up the equations. And so then I just calculated. M2, again, it's my question mark, it's my unknown, is going to be the mass M1, which is 1.7591 kilograms times the sine, I'm not going to write kilograms here because I'm doing some math here, times the sine of the angle theta, and the angle theta was 23 degrees. And then I just grab my trusty calculator. This is my favorite calculator. It's not the one that you need to have. I do recommend having a physical calculator, not using your phone. You're not going to be able to use your phone on the AP exam. You're not going to be able to use a computer-based calculator on your AP exam. You don't need a graphing calculator. You don't need to go out and spend $200 on a calculator. This is like an $8 calculator, and it's the one that I always use. I can't even remember the last time I used a graphing calculator. I don't find them as useful as maybe you might find them in your calculus class or your pre-calculus or even your algebra 2 class. But I am going to punch those numbers in here. So when I do this, when I multiply the sine of 23 degrees times 1.7591 kilograms, I get 0.687. So that means that mass 2 needs to be 0.6873 kilograms. So if this works, then if I put 687.3 grams or 0.6873 kilograms on this mass hanger, including the mass of the mass hanger, then we should balance. So I'm going to use my scale again. And on that mass hanger, I'm going to put some of these guys until I get to that magic number. All right. So I'm going to start with a 500 grammer. The mass hanger itself is about 50 grams. So it's about 549. So I think we need another, I'll put 100 grams, and then 50, and then, oh, that's a little too much. So I'll start putting on a couple 20s. Need some more here. 668, I want 6, yep, so another 20 grams. That's 688. That's a little too much. My mental math, if you haven't noticed already, is pretty terrible. Should be a little better at this. 687, so we need a little more. 680, right there. That's good. So if this is right, if my calculations are correct, when I hang this mass, this cart should not move. And sure enough, it doesn't. And again, I bypassed the whole guess and check or trial by error. I calculated that so that I knew it was going to remain at rest. Now, what's cool about this little experiment is Newton's first law says that an object in motion will continue to move in straight line constant velocity motion. So if the forces are in fact balanced here and I give this guy a little nudge, he'll keep moving down the ramp at pretty much constant velocity until the mass hanger hits that. Or push it up. Look, constant velocity. About constant velocity. Too bad we're hitting the table here. Let's try that one more time. So net external force is 0, remains at rest, continues at constant velocity motion. Now, if you got a discernible eye, you might see that it's not moving in exactly constant velocity motion. You'll see that it's actually slowing down a little bit, and that it's actually slowing down a little bit as it moves downward. And you might want to take that into consideration. That doesn't mean my calculation wasn't good. That just means there are factors that I didn't take into account. What I did here, this is the theoretical value for M2 if there were no other forces. But you might think there's probably some other forces that I'm not taking into account as the object is in motion. I'm going to leave that for you to think about. But yeah, there is a reason. There is a reason there. Now, just to show you, I'm just going to take off a little bit of this mass, and you'll see when I take off a little bit of the mass, it actually accelerates downward. So my calculation was done pretty well. I put the mass on, it remains at rest. I just take a little bit of it off, just a little bit of it off, and it starts accelerating down the ramp. And the opposite is true as well. The opposite is true as well. If I put a little extra mass on it, then it will accelerate up the ramp. Okay. So it's a nice little introduction to forces and how to do a physics problem. If you're in the laboratory setting, making measurements is key. Making careful measurements is key. Diagramming the situation is also very, very important. And then doing your calculations, setting up the equations, and doing your calculation. Now you might ask, well, why is this important? Why even do this? Well, if you're building something and you don't want that thing to collapse, if you don't want that thing to fly apart, you got to make sure that there's no net external force. When your car engine is going, when you're driving your car, that car engine, there's a bunch of moving parts in there. But so there's a lot of forces inside of a car engine that get your car to move. But the car engine itself, when it's running and your car's not moving, you don't want that car engine to fly apart. So you got to make sure that the net external force on that car engine is 0. The force is balanced. Otherwise, it flies apart. You throw a rod and your car engine breaks down. Also, the building that I'm standing in, the buildings that you're standing in, you got to make sure that when the engineers design those buildings and when the construction workers build those buildings, you got to make sure that those buildings have a net external force of 0. Otherwise, they won't remain at rest. And when a building isn't remaining at rest, it's obviously falling apart. So, yeah, brief introduction to Newton's first law. Again, we're not going to see this for about a month. So don't worry too much if this seemed a little confusing. But this is something that you're going to learn how to do. And hopefully we'll get some labs. If we're not going to do physical labs like this, we have a nice online program that we can do some online labs where you'll actually still have to make measurements and make predictions and do calculations and things like that. Well, that's about it. Have a good day, guys.